Hey guys, I'm Jade. Today is my LeetCode review one-take vlog on 230th problem. Kth smallest element in a binary search tree. We are given the root of a binary search tree, an integer k. We'll return the kth smallest value of all the values of the nodes in a tree. Let's example 1 here to understand this problem easily. K is 1, so we have to find the first smallest value, which is node 1 here. And in example 2 here, we need to find the third smallest value, which is 1, 2, 3. So the output is 3. Then let's get started to the intuition and the idea to solve this problem. First, we should know the binary search tree in order property. Binary search tree in order property, which is an in-order traversal of a binary search tree gives the node values in ascending order. So the kth element visited during this traversal is the kth smallest element. Then we'll use the several traversal options like recursive in-order traversal, iterative in-order traversal, or Morris in-order traversal to traverse the tree in order. And we'll keep a counter. When the counter reaches k, which means we have found our kth smallest element. Then let's get started with our recursive in-order traversal first. First, we'll declare several variables to help us solve the problem. Private, integer, count, started at 0. And this variable will count for visited nodes during the in-order traversal. And the second one, private integer, kth smallest value, started at -1. And inside the kth smallest method, first we'll start the in-order traversal. We'll declare the in-order method with 2 parameters. First is the tree node. We'll pass root node first. And the second parameter is k. And after the in-order traversal, we just return k smallest value. Then we'll implement the in-order method. Private void in-order method with 2 parameters. The first one is the tree node, and the second one is the k. And inside the in-order method, we need to handle the bad case first. If node equals null, we just return. Then we'll traverse its left subtree in-order method with node.left and k. Then we'll do an early termination check before processing the current node. If we have already found the kth smallest in the early recursion, we just return immediately. If kth smallest value is not equal to -1, which means we have already found the kth smallest number. So we just return immediately. Then we'll process the current node. First, we'll increment count variable by 1, and we'll check if count equals k. If so, we'll update kth smallest value to node.value. And we'll return. And the final part, we'll continue by traversing the right subtree. So we'll recursively call the in-order method with node.right and the k number. And that's all of the code. Let's submit code and then we'll analyze time and space complexity. Yes, our code got accepted. So the time complexity is big of n, as in the worst case, we'll visit each node only one time. And for the space complexity, it is big O of h for the recursion stack, and h is the height of the binary tree. And in the worst case, if the tree is a skewed tree, so h could be n and is the number of nodes in binary tree. And then let's get into the second approach, which is the iterative in-order traversal using a stack. First, we'll initialize an implicit stack to store nodes. So the code is stack of tree nodes. Let's call it stack. We'll create a new empty stack into this variable, and then we'll create a tree node variable called current, started at root node. Then we'll iterate this binary search tree until we process all the nodes. The code is while current is not equal to now, or stack is not empty. And inside the while loop, first we'll implement another while inner loop to push all the left children of the current node onto the stack to reach the leftmost node of the current subtree. While current is not equal to now, then we'll push the current node into the stack. We also have to update current node to current.left. Then we'll process the node at the top of the stack, which is the next smallest element in the in-order traversal. So the code is current equals stack.pop, and we'll decrement k to found one, as we found one more smallest element. Then we'll check if k equals 0. If so, which means the current node is the kth smallest. So we'll return current.value. Next, we'll move to the right subtree to continue this traversal. And code is current equals current.right. And out of while loop, we'll return -1 as a fallback. But this case shouldn't happen if k is valid. And that's all of the code. Let's submit code, and then we'll analyze the time and space complexity. Yes, our code got accepted. So the time complexity, it is still big O of n. In the worst case, we'll traverse all the nodes for only one time. And the space complexity, it is big O of h. H is the height of the tree. We use spaces for the stack. And in the worst case, if the binary search tree is a skewed tree, then h could be n. And then let's get into the final but best solution, which is Morris in-order traversal. First, we still have to declare several variables to assist us solve the problem. Let's say tree node named current started at root node, and then we'll create a count variable started at 0 to count for the number of processed nodes. Then we'll begin a while loop that continues until the current node is null, while current is not equal to null. And inside value, if there is no left child, we will process the current node by incrementing count and check if is the kth smallest. If current dot left equals null, which means the current node has no left child. So we'll process this node. First, we'll increment count by 1, and then we'll check if count equals k, which means we have found the kth smallest value. So we'll return current dot value. Then we'll check if the current node has real right subtree. If so, we'll move the current node to the right subtree to continue this traversal. Otherwise, the current node need to backtracks to the next in-order node by a temporary link. For these two situations, their code are the same, which is current equals current dot right. And on the other situation, if the current node has not now left subtree, first we'll need to find the in-order predecessor of the current node, which is the rightmost node in the left subtree. Let's create a predecessor tree node variable. Predecessor. So starting at current dot left. Then we'll create an inner value to find the in-order predecessor, which is the rightmost node in the left subtree. While predecessor dot right is not equal to null, and predecessor dot right is not equal to current. So we can avoid endless loop. And inside the inner value, we'll update predecessor to predecessor dot right. Then we'll check if the thread exists or not. If the thread doesn't exist, we'll save the thread, which is the temporary link, and move to the left subtree. The code is if predecessor dot right equals null. Then we'll create a temporal link from predecessor to the current node. Predecessor dot right equals current. And we also have to update the current node to current dot left to continue this in-order traversal. And on the other hand, if the predecessor does have a right subtree, which means this is the second time we visit this node, and the left subtree has been processed. So we need to remove the thread or remove the temporal link, and the code is predecessor dot right equals null. And then we'll increment count and check if the count equals to k. If count equals to k, then we'll return current value, as that's the kth smallest value. And we have to check if the current node has real right subtree. If so, we'll move to the right subtree. Otherwise, the current node need to backtrack to the next in-order node by a temporal link. And their code are the same, which is code equals current.write. And out of the outer value, we'll return -1 as a fallback. But this case shouldn't happen for valid k. And that's all of the code. Let's submit code and check for the correctness. And then we'll analyze our time and space complexity. Yes, our code got accepted. And the time complexity, it is still big of n. As we visit each node, put n at most twice. But the space complexity is the best, which is big of 1. As we didn't use any extra space for stack or recursion, we only use several constant variables to assist us. And that's all the solution for this problem, Kth smallest element in a binary search tree. You can also visit my online GitHub page here, which contains all the problem description, main idea, codes with very detailed explanation, and final time and space complexity analysis. And you can also visit my GitHub repository here, which contains all the code and nodes to build this online GitHub page. And I'll put those 2 links on my YouTube description below. And thank you guys for watching. I'll see you next time. Bye bye.